So let's say that we have a particle of mass m that obeys the following potential. And it is in a state which is the state that we saw before in the previous problem, some combination of the first three states, so the lowest energy eigenstates. And this is the combination. These are the weights. And we want to know what is the probability of finding, what's the probability of getting an energy h bar omega naught over 2. And the answer, of course, is related to this coefficient. It's just 1/4. And the probability of measuring an energy, so this is E0, whereas E1 is 3 h bar omega naught over 2, and the probability of that is that squared, so it's 1/2. And the probability of measuring E2, which is 5 h bar omega naught over 2, is 1/4. And of course, we can see that 1/4 plus 1/2 plus 1/4 is equal to 1 from normalization. So what happens if we measure the energy? Well, we're going to get this probability of getting this value of energy. So let's say that we end up getting, in fact, that value of energy, so we are in the ground state. What happens to our state? Well, of course, we now have, well, if we write the full time-dependent state after that, we just have psi naught 0 e to the minus I omega naught t over 2. Let's say we measure the average value of x, the expectation value of the position in time. Of course, there's no time dependence here. We are in an eigenstate. And the answer is 3, because the lowest point here is 3. So our potential has a minimum at x equals 3. So it's just a shifted simple harmonic oscillator.